Collision. It is an isolated event in which two or more colliding bodies exert relatively strong forces on each other for a relatively short time. There are two key rules of collisions are that first, law of conservation of linear momentum and law of conservation of energy. That means whatever type of collision will be there, in that collision the every collision will follow the law of conservation of linear momentum and law of conservation of energy. Now we will see the types of collision. Collision between particles have been divided broadly into two types. First is the elastic collision and second is the inelastic collision. Now we will define elastic collision. In elastic collision we will see here that is a collision in which there is absolutely no loss of kinetic energy. That means the kinetic energy in this type of collision will be conserved. So this is called elastic collision. For example, collision between atoms and subatomic particles are elastic collision. Practically, collision between two ivory balls can also be taken as an elastic collision. Okay, now we will see here the basic characteristic of an inelastic collision. So in the basic characteristic of inelastic collision, we'll find here first of all, as already told to you, whatever type of collision will be there, they will follow the law of conservation of linear momentum and the law of conservation of energy. Okay, so here in this collision also, that means in the elastic collision also, the linear momentum is conserved. This will conserved as in every collision. And second, the total energy of the system is conserved. This is conserved. And the third characteristic you can say, that is the kinetic energy is conserved. That means total energy is already conserved, but kinetic energy also will be conserved, because in the definition itself we have seen the elastic collision is the collision in which there is no loss of kinetic energy. So obviously the kinetic energy will also conserved. So these are three basic characteristics of an elastic collision. And the fourth one is also there, that the forces involved during elastic collision. The forces involved during elastic collision must be conservative force. it must be conservative force. Conservative force already we have defined, that means the force in which the work done in this force will be always depends on the initial position and the final position. As we have seen in the case of gravitational force, the work done to shift any of the object from the ground to some height h will be mgh in all the cases wherever path we will follow, but always the work done will be same for shifting the object to h height. Okay, that is, this is conservative force. So here in this elastic collision, the conservative force must involved. Okay, so these are the basic characteristics of the elastic collision. Now we'll see inelastic collision. In inelastic collision, this is the second type of collision, that is inelastic collision. In this we will see here definition first. In the definition, that is a collision in which there occurs some loss of kinetic energy. Some loss of kinetic energy is called inelastic collision. So the basic difference between elastic collision and inelastic collision is that in the elastic collision there is no loss of kinetic energy is there, and in the inelastic collision there is some loss of kinetic energy will be there. Okay, so this is the basic difference between the elastic collision and the inelastic collision. So now we'll see here, like, as there is always some loss of kinetic energy in most of the collisions, so therefore collision we come across in daily life are generally inelastic. You may observe whenever any collision take place in the daily life, we always find that the some heat produce, that means the heat produce or the sound produce. So some of the energy is lost in the form of heat, sound, etc., and so that the loss of kinetic energy will be taking place. Okay, so obviously all the experience, that means of the collision in the daily life is always must always inelastic collision. Okay, so if two bodies stick to each other after colliding, the collision is said to be perfectly inelastic. For example, mud thrown on a wall stick to the wall. The loss of kinetic energy of mud is complete and the collision is perfectly inelastic. So this is one indication that if any of the inelastic collision will take place, that means the bodies will stick to each other, and that means they will move with the same velocity. Okay, so similarly when an arrow gets stuck in a target and the two move together, the collision is perfectly inelastic. Likewise, if a meteoroid collides head on with earth, it often gets buried in earth and the collision is perfectly inelastic. Okay, so these are the some example of the daily life that we may observe, and these are the example of inelastic collision. Basic characteristics of inelastic collision. First, the linear momentum is conserved in inelastic collision. The total energy of the system is also conserved. The kinetic energy is not conserved. Already discussed that the kinetic energy can be changed in the form of heat energy or the sound energy. And the fourth characteristic is some or all the forces involved in an inelastic collision may be non-conservative. That means it may depend on the path. It is that means it is not independent of the path. Okay, so the work done will be depend on the path by applying this force. So these are called non-conservative force, and the non-conservative force are involved in the inelastic collision. After that we'll see coefficient of restitution. Coefficient of restitution. Or we'll call it coefficient of resilience. Represented with letter E. We'll define it. The coefficient of restitution or coefficient of resilience is the ratio of relative velocity of separation after collision to the relative velocity of approach before collision. For example, we'll see here, suppose an object of mass m1, another object of mass m2. m1 is initially moving with velocity u1 and m2 is moving with velocity u2, and after collision, suppose these two objects are moving with velocity v1 and v2. That means after collision you will see that this object, they are separating with the velocity v1 and v2. So in such situation, as we define here, the coefficient of restitution, that means E, is what? It is the relative velocity of separation. This separation will take place after collision, and upon relative velocity of approach, that is before collision, when both the objects are approaching to each other. So before collision, this is the relative velocity, and we can see here this relative velocity is v2 minus v1 upon, this is u1 minus u2. What we observe here, this is the relative velocity, v2 upon v1 is the relative velocity of separation of the two objects, and u1 minus u2 is the relative velocity of approach before collation. And we find that for perfectly elastic collation, the relative velocity of separation after collation is equal to relative velocity of approach before collation. That means what we can say, for perfectly elastic collation, for perfectly elastic collation, this v2 minus v1 must be equal to u1 minus u2 or we can say the ratio of these two, because these are the same quantity, so the ratio of these two will be equal to 1. So for perfectly elastic collation, the relative velocity of separation after collation will be equal to the relative velocity of approach of before collation. Okay, and for inelastic collation, we'll see here, for inelastic collation, this is for inelastic collation, E is equal to 0. E is equal to 0 because the relative velocity of separation, relative velocity of separation after collation, collation is equal to 0. That means v2 minus v1 equal to 0, or you can say v2 equal to v1 or equal to v. Already we have discussed in the inelastic collation, both the object after collation stick to each other and move with the same velocity. So because v2 is also v and v1 is also v, so v2 minus v1 must be 0. That means the relative velocity must be 0. So the relative velocity after collation here is 0, and that's why E, which is equal to v2 minus v1 upon u1 minus u2, that is equal to 0, u1 minus u2, and that is equal to 0 here. So for the perfectly inelastic collation, E is equal to 0. That means if we are taking here for all other collation the coefficient of restitution or the coefficient of resilience, we'll say here that E lies between 0 and 1. That means we can say E is greater than 0 and equal to 1. But E can be equal to 0 for the perfectly elastic collation, and for the elastic collation E is equal to 1. So this way we'll note that already, as we have discussed about the collation in the system that are closed, that means for the isolated system we are discussing here, and for the isolated system only we are talking about the law of conservation of momentum and the law of conservation of energy. So that is, no mass enters or leave the system, and further the system are isolated, that is, no net external force act on the bodies within the system. In fact, external forces, that is gravity and friction, are negligible, small compared to the strong impulsive forces during collation, and which are internal forces. Elastic collation in one dimension. It involves two bodies moving initially along the same straight line, striking against each other without loss of kinetic energy, and continue to move along the same straight line after collision. We'll see here, suppose the two balls A and B of masses m1 and m2 are moving initially along the same straight line with velocities u1 and u2 as shown in figure here. And here you will observe when u1 is greater than u2, the relative velocity of approach before collision will be u1 minus u2, and therefore the two balls collide. This is during collision it is, and let the collision be perfectly elastic. So after collision, suppose v1 is the velocity of A and v2 is the velocity of B along the same straight line, and here you will find the relative velocity of separation after collision will be v2 minus v1 when v2 is greater than v1 here. So what we observe in this situation, because it is one dimension elastic collision, and since it is elastic collision, the linear momentum will say, since collision is elastic, so the linear momentum will be conserved, and linear momentum before collision must be equal to linear momentum after collision. Linear momentum after collision. So that, just to follow the law of conservation of momentum, now linear momentum before collision will be m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. We can just take m2 common here. You will see that m2, this is m2, will take m2 u2 that side, so it is v2 minus u2, and this one is m1 u1 minus v1. This will write as equation 1. And one more characteristics we have seen of the elastic collision, that total kinetic energy of the system will be conserved. That means kinetic energy before collision must be equal to the kinetic energy after collision. So what we'll observe here, the kinetic energy before collision is half m1 u1 square plus half m2 u2 square is equal to half m1 v1 square plus half m2 v2 square. We'll take out half common here, or you can say simply we can cancel out half because both the side half is here, and we'll take out m1 terms in one side. So we'll find here that m2, and this is v2 square minus u2 square upon m1, it is u1 square minus v1 square, and we'll find this is equation 2. Now what we'll do here, just will divide equation 2 from equation 2 by equation 1. So when we divide it, equation 2 divided by equation 1, equation 2 is m2 v2 square u2 square is equal to m1 u1 square minus v1 square, and divided by equation 1, that is m2 v2 minus u2 equal to, it is here, so I'm just writing equal to in the midway only, divided by, we'll see this is m2 and sorry no m1, it is not m2, it is m1 m1 u1 minus v1. So you will see that m2 will be cancelled, m1 will be cancelled, and this v2 square minus u2 square can be written in the form of a plus b, a minus b. So it must be v2 minus u2 and v2 plus u2 upon this is v2 minus u2. This is also just apply the identity a minus b, a square minus b square is a minus b, a plus b. So here also we'll get the same thing, u1 minus v1 and u2 plus v2. This is equal to, divided by u1 minus v1. So v2 minus u2 will cancel here, u1 minus v1 will be cancelled. Now it will become v2 plus u2 is equal to u2 plus, this is u1, it is, this is u1 and v1 it is, because u1 square minus v1 square is u1 minus v1 and u1 plus v1. So this must be u1 plus v1. Okay. Now what we'll see here, that is v2 minus v1. Just transfer v1 this side and u2 will take that side. So it is u1 minus u2. Or what you can say here, this is what? This is relative velocity of separation. This v2 minus v1 is relative velocity of separation after collision, and this u1 minus u2 is relative velocity of approach, before collision. Okay, now what we'll find, it came relative velocity of separation after collision is equal to relative velocity of approach before collision. That means v2 minus v1, u1 minus u2, the ratio of these two will give us 1, and this is actually E, and this is the coefficient of restitution. So what we derived here, we have derived for the perfectly elastic collision, the coefficient of restitution in one dimension is unity. Calculation of velocities after collision. So for the elastic collision in one dimension, we are now going to calculate the velocities after collision, that means the value of v1 and v2. So to calculate the velocity of A, that means the v1, we'll just take from equation 3, and equation 3 is, as we have derived the formula, this is V2 plus U2 is equal to U1 plus V1. Okay, so from this formula we'll see here V2 plus U2 equal to U1 plus V1, and we'll just transfer U2 that side, so it become V2 equal to U1 plus V1 minus U2. Now we'll put this value, put value of V2 in equation 1. You can see equation 1 here. The equation 1 is M2 V2 minus U2 equal to M1 in the bracket U1 minus V1. So here we'll put the value of V2. So first of all we are writing the equation 1, that is M2 in the bracket V2 minus U2 and equal to M1 U1 minus V1. In place of V2 we are writing here the value U1 plus V1 minus U2, and this is minus U2. This minus U2 is also there, and equal to M1 U1 minus V1. Now M2 will find U1 plus M2 V1 minus, this is 2 times M2 U2, this is M1 U1 minus M1 V1. We'll take M1, this M2 V1 from this equation, and that side minus M1 V1 is there. We'll transfer this side, so this will become plus M1 V1. We'll write M1 V1, and rest of the quantity will transfer this side. So already it is here M1 U1. Now it is minus M2 U1 and minus 2 M2 U2. We'll take V1 common, so V1 is equal to M2 plus M1, or we can write M1 plus M2 also. This is M1 minus M2. We'll take U1 common, minus 2 M2 U2. So we are going to calculate here the velocity V1, and we'll just calculate this velocity in terms of U1 and U2. So we have transferred M1 plus M2, which will divide here in both the terms. This is U2. So this is the equation for the velocity of body A after collision. This will write as equation A. Now in the same equation, when we put the value of V1, so we'll calculate the velocity for velocity of body B. So once again from equation 3 we can write here, this is V2 plus U2 U1 plus V1. We'll just write V1, this is V1 is equal to V2 plus U2 minus U1. So we are going to substitute the value of V1 in equation. First, so the equation 1 is, the equation 1 we have calculated here is M2 V2 minus u2 equal to m1 u1 minus v1. We'll put the value here of v1. This is v2 minus u2 m1 u1. This v1, the value of v1 is, we have calculated it, u2 v2 plus u2 minus u1. So here we'll write u2 plus v2, that minus plus will become minus v2, and we have written minus u1, that will become plus u1. Okay, so this way the sign also change. Now m2 v2 minus m2 u2 is equal to m1. You can see that u1 and u1 will become 2u1, so it is, we can write 2m1 u1 minus m1 u2 minus m1 v2. We'll take this side m2 v2 and this minus m1 v, this is minus m1 v1, it is v2. Okay, so plus m1 v2 here, this minus m1 v2 will transfer this side, plus m1 v2 here, and is equal to 2m1 u1 minus m1 u2 plus m2 u2. So here we'll take common v2, so v2 is in the bracket m2 plus m1 remain, or we can write m1 plus m2 here. This is equal to 2m1 u1 minus, will take common, so it is m1 minus m2 in the bracket, and u2 we can take common here, so it is v2 equal to 2m1 upon m1 plus m2 u1 minus m1 minus m2 upon m1 plus m2. This is u2. So this way we have calculated the velocity for the second body after collision, and after this we'll see many different cases in the next video.